Just do one example, and then let's just do one example. Unfortunately, not a complicated example, and maybe not persuasive as to why you would care about this just yet. But nevertheless, very important, because this is the quiz question which everybody gets wrong until they practice it. All right? So the integral from, say, 1 to x of dt over t squared. Let's try this one here. So here's an example of this theorem I claim. Now this is a question which challenges your ability to understand what the question means, because it's got a lot of symbols. It's got the integration and it's got the differentiation. However, what it really is an exercise in recopying. You look at it and you write down the answer. And the reason is that by definition, this function in here is a function of the form g of x of the theorem over here. And by definition, so this is the g of x. And by definition, we said that g prime of x is equal to f of x. Well, what's the f of x? Look inside here. It's what's called the integrand. This is the integral from 0 to x of f of t dt, right? Where the f of t is equal to 1 over t squared. So your ability is challenged. You have to take that 1 over t squared and you have to plug in the letter x instead of t for it, and then write it down. As I say, this is an exercise in recopying what's there. Right, so this is quite easy to do, right? I mean, you just look and you write it down, but nevertheless, it looks like a long, elaborate object here. Pardon me? So the question was, why did I integrate? Why did I not integrate? Very good question. Why did I not integrate? The reason why I didn't integrate is I didn't need to. Just as when you take the antiderivative, the derivative of something, you take the antiderivative, you get back to the thing. So in this case, we're taking the antiderivative of something and we're differentiating it. So we end back in the same place where we started. We started with f of t, we're ending with f, little f. All right? So you integrate and then differentiate and you get back to the same place. Now the only difference between this and the other version is, in this case, when you differentiate and integrate, you could be off by a constant. That's what that shift, why there are two pieces to this one. But there's never an extra piece here. There's no plus c here. When you integrate and differentiate, you kill whatever the constant is, because the derivative of a constant is 0. All right, so no matter what the constant is hiding inside of g, you're getting the same result. All right, so this is the basic idea. Now, I just want to double check it using the fundamental theorem of calculus 1 here. So let's actually evaluate the integral. So now I'm going to do what you suggested, which is I'm just going to check whether it's true. No, I am, because I'm going to just double check that it's consistent. It certainly is slower this way, and we're not going to want to do this all the time, but we might as well check one. So this is our integral, and we know how to do it. No, I need to do it. And this is minus t to the minus 1, evaluated at 1 and x. Again, there's something subliminally here for you to think about, which is that, remember, it's t is ranging between 1 and t equals x. And this is one of the big reasons why this letter t has to be different from x, because here it's 1 and there it's x. It's not x, so you can't put an x here. Again, this is t equals 1 and this is t equals x over there. And now if I plug that in, I get what? I get minus 1 over x, and then I get minus a minus 1. All right, so this is, let me get rid of those little t's there. So this is a little easier to read. All right, and so now let's check it. It's d by dx. So here's what g of x is. G of x is 1 minus 1 over x. That's what g of x is. And if I differentiate that, I get plus 1 over x squared. That's it. You see the constant washed away.